what I want to do here is I will, in fact, talk about a very similar topic. I will use the same algorithm that has just been presented, but to compute perturbation theories. So what I want to do in this talk is to compute perturbative expansions for different kind of problems, mainly for, first, an out-of-equilibrium problem, which we have been trying to solve for a while. And also, at the end of the talk, I will present more recent work about potentially a new generation of quantum impurity solver with this technique. So there will be some overlap with the previous talks. I'm sorry about that. So I will re-explain. Part of it will be re-explaining the same algorithm, but I can maybe go a bit faster. So the first problem we have is, in many cases in physics, we have large dimensional integrals. So imagine I have a function I want to integrate in more than let's say 10 dimensions or more, or a discrete sum, which for all the purposes of this presentation, I will consider the same because I can always take a one-dimensional grid, a Legendre grid, a Curtis-Crenshaw grid, just with d points and discretize. The problem, obviously, is that if we do it naively, we have the curse of dimensionality, it blows up exponentially with n. And the standard answer in many of our methods is to go to Monte Carlo. The idea which has been presented here is, in fact, to use tensor network to perform this integral. And all this work has been really inspired by this paper, by the previous speaker. The point is that if my function in n dimension can be written as a matrix product state, meaning f here is equal to the product of m at different points where the physical legs are the variable of my functions with some rank chi, bound dimension, except, of course, at the boundaries. And if I can do that by controlling the error with the algorithm which we have just seen, then it's very easy to integrate. Because I can integrate each variable separately. In other words, I have separated my variable. If my rank is 1, my variables are separated. If it's more than 1, well, I have to compute all the matrices, and then I do the matrix products at the end. So this looks a very appealing technique, especially because, and as we will see, it also works for functions that are oscillating a lot, and I will show you an example. The real question is your function compressible in an MPS? And that's, of course, very problem-dependent. But if it is, then we have an algorithm to reveal it. Well, there's the algorithm that has just been presented before. And then we can do the integral. And I want to do that for a specific kind of problems, meaning for computing perturbation theory. In other words, I want to compute high-order perturbation theory for fermionic problems, let's say an interaction, power of the interaction, for some physical quantity Q, can be a charge, density, grain functions, current. So my expansion is, finite order expansion here, Qn u to the n, and we know, textbook, that Qn is indeed an integral and the sum of some function, small qn, over times and positions, and the Qn is the sum of all Feynman diagrams for my quantity at order n. And there's been a lot of activity in our field by a subgroup of the field, part of the field, called diagrammatic quantum Monte Carlo, following ideas by Prokofiev and Swistunov, which goes basically as follows. You compute Qn with Monte Carlo techniques, and the name, where Qn sum all the Feynman diagrams. Originally, in the original proposal, the diagrams were explored stochastically. More modern versions used, resum expression for the Feynman diagrams that can sum all of them in exponential time, not factorial. 2 to the n out of equilibrium, 3 to the n in equilibrium. And we have done that recently. And the second part is, as soon as you have the series, you try to make sense of the series by summing it. The difficulty, of course, is that the series is in general not convergent, apart from weak coupling. And there are techniques to deal with that. So the issue that we have in this field, and there are several issues. First, speed. Why do we want to go beyond Monte Carlo? Because Monte Carlo is slow. We want to have higher precision, especially when you want to resum series. You need to have more and more precision on Qn the higher you go, because it's very sensitive. And also there are cases, we will see one in out-of-equilibrium case, where the function can be really oscillating. And as we know, that's very bad for Monte Carlo. That's one manifestation of the sign problem. So my goal here today is I want to replace Monte Carlo by this tensor integration techniques, and I call that tensor train diagrammatics, and see how far I can go. Okay, that's the goal. But before this, I go into detail, especially in this audience, perhaps I want to emphasize that perturbation theory can give a lot more than weak coupling. I mean, there has been several examples over the recent years where generating this higher order perturbation series, and here by high, because of the 2 to the n scaling, let's say 10 to 20 orders, we can actually solve exactly some problems, even in strong coupling regimes. There's been beautiful work doing that in equilibrium. For example, the work of our former CCQ postdoc, Riccardo Rossi, on unitary gas, and in comparison to what you can do, for example, in cold atoms experiments, where you can generate the series. It's a non-divergent series. You can Borel sum it, and so on. More recently, very nice work has been done. So also in collaboration, between Riccardo and the group of Paris at Collège de France, solving, use this technique, some point in the pseudogap regime at finite temperature and the Hubbard model, which is, quite remarkable. And today I will discuss a different problem on which I've been working over the last years, meaning out of equilibrium problem, and I will start with a simpler problem, quantum dot, or an impurity model, pushed out of equilibrium. You put a, kind of dot, you put current through it, and you push it to out of equilibrium. And what I will show you is that these perturbative techniques works even at long time. There's no time limit. In steady state, even in strong coupling regime. You can capture Kondo effect and many of the physics. The last part, and I will come back at the end of the talk, is that in the quantum embedding techniques, we use a lot these quantum impurity solvers, and the standard algorithms to do that is the quantum Monte Carlo algorithm, continuous time quantum Monte Carlo algorithm. And these algorithms, in fact, perform also a very high order expansion of the partition function. So the next question will be, can we replace these also by tensor network, and at which cost? So that's a bit of motivation. Now let's go to a real concrete case. I want to consider a quantum impurity model in real time out of equilibrium. So, okay, just to fix my notations, and what I mean by quantum impurity model is a few quantum degrees, interacting degrees of freedom, a couple of shell in an atom, or even a single spin 1/2, which is coupled, like in this little picture, to a bath of non-interacting electrons. So why are these problems interesting? First, because they exhibit strong correlation physics. There's the Kondo effect, for example, meaning the screening of a spin by the Fermi sea. Second, and you will see that in the bench, for some of the system in some limits, we have an explicit analytic solution by better ansatz. So we can compute to any order on any precision the expansion. So we'll be able to test our techniques in a non-trivial case. But that's important. And of course, we want to use them. They are building blocks as quantum embedding techniques like GMFT in equilibrium, out of equilibrium. And of course, they are also realized in nanophysics through many realization of quantum dots. So there are experiments we can try to match with precision. To be precise, the model I'm going to consider here is the simplest, the Anderson model, where you have one little dot here. Can one see? Yes. With a gate level, epsilon d, which is coupled to two leads, left and right, across which you can put a voltage. Therefore, there is a current through the dot. And you have an interaction on the dot, and the electrons are non-interacting. The leads are non-interacting. So the question which we want to ask, are all sorts of questions. How can we compute the spectral functions? Can we get the Kondo temperature? Can we get the currents through these problems? We understand the physics of this problem for more than 20 years. Here we want to have high precision calculation at any temperature, any voltage in steady states. We want to be able to match this experimental curve, for example, as a function of voltage and epsilon d for many parameters. So we need quick methods as well just to do that. That's why we are looking for quicker and quicker systems. All right, so that's what I said before, but just to say it again, what I want to do is perturbation theory at finite time, compute Qn, that's what I'm going to discuss. The part I am not going to discuss, which is discussed in previous works, is how do I sum the perturbative series. Just say a few things here. At finite time, the series is convergent for any u, because it's a finite volume system. In steady states, we can go to infinite time. The series has a finite radius of convergence, but we can deal with that by changing variable in the conformal change of variable in the U-plane. And in the problem in question today, will allow me to compute even to U equal infinity with a perturbative expansion. So today I'm going to concentrate on how do we compute Qn. But before I do that, I'm going to show 2 slides of results, which we have already obtained with the Monte Carlo, just to show that we are starting from something, from a method that works, and we want to improve it and then push it to other methods. But just to put some graph in front of the words which I have said. So you have a quantum dot. First, we can benchmark in equilibrium. Can we really do things with perturbation theories? Because it makes no sense to compute all of these perturbative series if at the end I can do nothing with it. So I want to show that indeed we can. Can I compute the spectral function? So yes, that's a spectral function, as a function of frequency of very, very low temperature. You see here the Kondo resonance, which is characteristic of this, the strong correlation physics here in the systems, on top of the NRG, which is the golden standard for this kind of problem here. We see that we have an excellent match, including at relatively high interaction. The width of this resonance at the Kondo temperature, we can plot it here as a function of the interaction U, that's the red curve, which we have. And again, even at large U with techniques and proper resummation, you are on top of the NRG calculations. However, if you don't do any resummation and you are naive about summing your series, you will get the green curve, the blue curve, if you start truncating your series at different orders, meaning there is a radius of convergence here. I mean, the resummation techniques I mentioned allows me to go further. So yes, we can do equilibrium calculation with this technique. We can also do non-equilibrium calculation with exactly the same technique. That's again the Kondo resonance. It's the same graph as a function of frequencies, but stacked for all different values of U's in a color plot. So if you take a slice, an horizontal slice, you'll get the graph I had before. You can see the formation of the Kondo resonance here, close to the arrow. You have a very, very narrow resonance at origin without interaction. It gets narrower and narrower exponentially, and it splits here because of the voltage at large voltage and being destroyed by non-equilibrium effect. This is a finite voltage calculation, low temperature. And the point I want to emphasize, this calculation is one calculation because I have the series, so I can, as soon as I have my perturbative series, I can compute the whole thing at once. Other things we can do real non-equilibrium things like the distribution function of the electrons on the node, on the dot. How different is it from a thermal function, from Fermi function? It would be a Fermi function in thermal equilibrium. Out of equilibrium, it's not. It's some function. Without interaction, it's known. It's a 2-step function. That's basically the average of the 2 Fermi functions in the leads. What happens when you put interactions? Well, it's something. It's non-thermal. It has a discontinuity, but smaller, and it has this form. By the way, here, this is a calculation at U equal infinity. Same with perturbative techniques. So just to show that we can already do things, but of course, we have selected a bit the problem because in many, yes, sorry.
Are the oscillations physical, or is that
no.
where you're starting to have the
No, it's a noise problem.
Okay.
Noise plus amplified by resummations. So that's precisely one of the needs for higher precision. And there are, of course, other regimes of parameters where we can't do it because the calculation will lead to very oscillating integrals. So, of course, we have a bit selected regimes where we can do this. That's why we try to do better. Now let's go more into the detail. As I said, we need to integrate some function. This is small. This is just, let's say, the charge on the quantum dot or anything, in fact. You can write it as I said, a sum of Feynman diagrams. So on the Keldysh contour, you take the double contour times Ru's. Keldysh indices are alphas, plus or minus 1, and you start at some time t0, you measure at time t, okay? Textbook. We know that Qn can be written as an integral over the sum of Wick determinants made by the Beer-Green functions, and you need to sum of the Keldysh indices and integrate. Now, 2 points here. The first point is that this expression shows, and that was not realized early on, that you need to do the sum of the calculation indices explicitly here, that costs you 2 to the n, because there are 2 to the n indices. If you do that, there are massive cancellation in this sum, which makes that the integral will be completely localized around the time t here, where you want to do the integral. So the integral is localized around t, which means I can push t to infinity immediately, and I can go to steady states. There is no problem going to long time. The price I'm going to pay is that I need to resum the series now. But sometimes I can do it. This, by the way, is the shape of the green function, the bare green function, which I'm going to put in this determinant. That's how it oscillates as a function of time in some problems. And I have that in 20 dimensions. So, sometimes Monte Carlo has trouble with this kind of thing. And it costs me 2 to the n to evaluate, which means I have an integral where the cost of evaluating my function is very high. So I need as few points in my sampling techniques, to do it. And the point of my talk here is basically on this slide. The point is that this Qn function has an MPS factorization. And that's the main result. So it's factorizable, but not as a function of time, but as a function of time differences. We are in a time-ordered problem, so I can order my times. And I need to consider my function as a function of time differences, v's, not the times u's. As a function of v, yes, it is an MPS. Here is the plot of the function versus its MPS interpolation. The exact curve is the orange curve. The blue points are, the MPS interpolation with a rank 30, which is very low, 0 temperature in this problem. As you can see, it fits quite well. We took 1 point at random, so we just did the calculation. So the key question is, how do you reveal the MPS factorization? And to do that, I will need exactly the algorithms that Dimitri has explained before, the tensor cross interpolation. So before I go back to results, I will open a little parenthesis just to explain this algorithm. And then I will show, how the integration really works in that case and what we can do with it. So before I go there, I just want to emphasize, maybe it's clear already, but this is a very different use of tensor network than, the standard DMRG or PEPs. And the reason is that what we're trying to do here is to do a compression of a function, which is not a wave function. I'm not considering wave functions. I'm considering an n-body correlation function. I'm not making an answer that my function is known. I know it very well. The only thing I want to do is to compress it, to integrate it. So in some sense, it's a kind of machine learning, if you want. It's a fit. And we will see the consequence of that. So tensor cross interpolation. Okay. The executive summary, if you want, of the algorithm is the following. Give me a tensor A, which has a low rank, where ui are discrete indices. The algorithm will build an MPS approximation, TCI, of rank I, progressively by doing sweeps. It will do it by evaluating the function A on n points, n being linear in small n, meaning the number of variables. D is the number of value of the index here. And chi square, which is the rank, which is, of course, much smaller than exploring the whole tensor. And it will do that with an error estimator, epsilon of chi, which I can plot. Here there are 2 of them. We'll show a bit later what. As a function of chi, and I can see when the algorithm progresses that my error decreases. Here, like 1 over chi to the 4. So I have an error estimate of my problem. So again, that's been shown before. That's the cross-interpolation formula for a matrix. If a matrix has a low-rank decomposition, the way to do that is you take some subset of pivots, some set of rows and column indices, big I and big J, 1 to chi, and you write your matrix in general for any indices as the products of slices in 1 dimension at the pivot position, the slices of the row at the other pivot position, and the inverse of the pivot matrix in the middle. And this has nice properties. First, it is exact when you evaluate it on the pivot that you've used. And second, if your matrix is of rank chi, it's exact everywhere. And in fact, there is a simple way to see that, which also tell you why you need to write this form, because it was, when first I saw it, it was not totally obvious to me, at least, is that if you take a submatrix of pivots which is invertible, if I add 1 more x and y, I will take a slightly bigger submatrix. By definition of the rank, if the rank is chi, the det is 0. But I can rewrite this det with a standard formula that it is a determinant of the big corner times this. And this determinant here, A, is non-zero by assumption, so this is 0. This is exactly the formula that we had before. So that's why you have this kind of form. Of course, you have to generalize that when you have epsilon ranks and all of this. This is just a quick argument. So that's for matrices. Now, what do we do for tensor? I mean, naively, what I can do, I have my tensor here, A. I can regroup all the indices but the first one together. Then I have a matrix, and I can apply the cross-interpolation for matrices. I get this, the first line. This is P, the inverse pivot matrix. And I see that my indices here will be multiplets of, indices. And, I will have this form. Then I can regroup the pivots ui with the other indices u2 and have another smaller tensor, which I can recursively decompose. This is not a practical algorithm, but it just gives you an idea why you are going to find the TCI form. So the TCI approximation is written in this way. The worst part in this is to find notations, because there are many indices of different types. So the tensor is written as a product of T tensors, the way we write it here, the orange tensors and the blue tensors. The blue tensors are just pivot matrices. So in these notations, pivots will now be multi-indices of length alpha or n minus alpha from the right and from the left. And the set of pivots will be set of multi-indices. And I called curl U the set of the original value of all the indices. Then with these notations, these P matrices are pivot matrices. They are just the evaluation of the function on the pivots. The T's are one-dimensional slice. I put everybody on the pivots, but one index, which is allows to run over the whole values here. And that's the vertical index here. And the formula says, the TCI approximation says that you just multiply the one-dimensional slice, they are here, and you put in between the inverse pivots. And you have all sorts of finite number of indices in between. The fundamental property in this is that all of these indices have to respect what's called a nesting property, which is written here, which loosely speaking is to say if I have my multi-index at some rank, I chop the last one, it is included in the pivots of lower dimension. And this ensures the property of interpolation, meaning that if you evaluate your TCI approximation on the one-dimensional slice, it is exact. It's giving you exactly the slice. So it's an interpolation on the whole one-dimensional slices. But of course, if you relax now two indices, two neighboring indices, you are not going to be exact. Pi being the two-dimensional matrix, which was the matrix which was presented before, slightly different notation, of course, to confuse everyone. Then you have a tensor and a function of two neighboring indices. You fix the other one to the pivots. And the approximation is that you're going to approximate these tensors by TP minus 1 again, fixing external pivots. And the error, which we're going to try to minimize, is precisely the difference between this tensor here and its TCI approximation. And by the nesting condition, one can show indeed that the same as approximating the whole tensor and the TCI approximation on the 2D slices. So the 1D slices are exact, the 2D slices are not, but you put pivots to minimize the error in 2 dimensions. So the algorithm will sweep over the tensor, take all the pair of adjacent indices, and add pivots to minimize the error systematically. Well, that's what this slice says. And it will keep the error that's found in the 2-dimensional slices as the error evaluation. Okay, there are different strategies to evaluate this. I'm not going to go into this. We tried several ones. It doesn't make much difference how to explore the 2-dimensional slice to find the pivots. In this problem, it's not very important. So yeah, just let me finish. Yeah, just to finish on that. So the error is precisely the maximum of the error on the slices and maximum on the sweeps, and that's the error estimator which we wanted to have. Yes.
Okay. So I'm not sure which slide this refers. It says, is there here a norm of a matrix on the right-hand side? Is there here a norm of a matrix on the right-hand side?
Right-hand side. But which slide?
Maybe Artem can type and say.
Which slide?
Artem, perhaps you can clarify which equation you're referring to.
So the epsilon.
Slide 23. Okay.
That's the maximum of the norm. The maximum on the, okay, correct. That's, this is absolute value because I put all the indices, I and U alphas. This is just an absolute value. So the error will be the maximum on all of that on the slices and on the I. But here it's just the numbers. They're just numbers.
Okay.
Because I put all the indices explicitly. So the maximum of that's exactly what this slide says, is the error as a function of chi. Max on the slides, max on the I, max on the sweeps. And it varies as a function of chi. So when you run it on the 10-dimensional integrals we have seen before, it decays. There are two different estimators. We'll discuss that in a second. Here as a function of chi. Okay. Now, there is one addition we did to the TCI. Until now, this is exactly the algorithm of the paper of Dolgov and Sebastianov. There is one little addition, at least as far as I am aware of, is we have the following problem when we do our integrals. We have functions with very long tails because contrary to the integral that was presented before, it's not on 0, 1 to the power d. It's not on a compact set. It's on R. And there are long tails. The function has long tails where the function is very small but on a very large volume. So if you approximate the function well, point by point, you will approximate it at the center very poorly in the tail, but the volume is big, so your error is going to be very big. So the way to do that is to reweight the error function by putting your approximation into the integral and reweight the error function by what would be the product of the tensors from all the left and all the rights. So it's just almost the same thing, except you put the right and the left in these. So the consequence of that is that if you want to have a function which has very long tail, one way to do this is to change variable. For example, to say that you want taking v over 1 plus v, that new variable will be compact, and you can do that. And what we see here is that, so with the ordinary functions, if you do a calculation here as a function of v with respect, compared to the calculation function of w, this is just the two dashed line, we'll see what I saw. I mean, it's much worse to do it in the original v variable because it doesn't converge well because of the volume. Yeah, I'm coming. Yes?
So you're talking about long tails of your functions.
Yeah.
Is your domain, the discretization domain you're using, infinite, or do you have a truncation on the domain that you use?
The time, it's finite but big because the time can be quite big. Especially at long time between the initial time.
But you have always a hard cutoff. So
yeah,
if you
but it's very far.
Okay. So, but you wouldn't capture polynomial tails in that case?
Oh, yes. In the function, you would. Yes. These are polynomial tails. Yes. At 0 temperature. Finite temperature, they would decay exponentially more. But you will have that. So if you use the ordinary error estimate, I mean, you will see that in the original variable, it decays much more slowly. But if you use the environment error, which is the second set of curves, you see that it doesn't matter in which variable you do it. So this kind of estimator saves you to find the change of variable, which is problem dependent. It makes your algorithm much more automatic. That's what this graph illustrates. And that's a little addition we did to the calculation. And the second thing is, all of this error calculation is, if you use the machine learning, it's an in-sample error. You are looking at the error at the slices which you are looking at. So what we looked in a couple of points is, okay, take the approximation that we have, take a point of maximum discrepancy by searching it in 7 dimensions, and plot from that point in all different directions. That's what we have here. The red star is the exact calculation. The blacks are the approximation with different chi, and you can see indeed that the outsample error is very small for chi, reaching about 40. So it's just you are approximating the function well on the slices, but in fact the function interpolates well on the whole domain because the function has low rank. But it's a good check to do. All right, this was about the algorithm. So it's another version of the same thing that was shown before. Now I want to show a few results. What happens if I put all of that together? So I take my approximation with TCI and I integrate. That's the result. That's the relative error at order 19. Why 19? I don't know, but 20, let's say, between the calculation here done and the beta ansatz solution, which we know with an analytic formula. We can expand that in Mathematica and have huge formulas. We can have any precision we want. As a function of the number of points which we need to compute the integral, we see it decays quickly, like 1 over n to the square. Compare that to Monte Carlo, which is 1 over square root of n. And this is the same graph for different orders, but this time as a function of chi. There is a relation between n and chi. It's basically n is chi square. So we'll see that at low order, it decays very fast. And high order, it decays like 1 over chi to the 4, 1 over n square. And more importantly, it's more or less stable when you increase the order. The property of factorization does not degrade when you go to higher order, which is, of course, a very important point. So we can reach precisions here, which, for me, we were doing Monte Carlo before, is, of course, unthinkable before. The only limitation here is machine precision, and then all of determinants, and, there's some errors. We lose some digits compared to floating precisions, but that could be fixed. That's what I said before. If I look now at fixed bond dimension, the error for, let's say, n equals 30, so 30 order in perturbation theory, as a function of the order, up to order 30, we'll see that the relative error does not significantly increase, meaning that the bond dimension does not grow with dimension. So you go to higher dimension, and then your approximation in NPS stays, more or less stable. Now, one of the advantages of the technique is that I can deal with very oscillating functions, and I wanted to illustrate that. The factorization has nothing to do with the average sign of the function. There is no reason why it should. And so we can vary one of the parameters of the model here, the dot level, epsilon d. If you change it, you will introduce oscillatory terms, and your integral will be very small, many of them. For example, the relative sign, the absolute value of the integral over the integral of the absolute value here, so the average sign, is plotted here as a function of epsilon d. If your particle holds symmetric, it's basically OK. If you go away from it, you can get a sign of 10 to minus 5 or worse. That's hell for Monte Carlo. You have 10 to minus 5. Your computation time will increase by 10 to the 10. If you do that. Now, if I fix the bond dimension of my factorization error for the same function, you see that as a function of this parameter epsilon d, same parameter, nothing happens. So my function still factorizes. It oscillates a lot, but it still factorizes. That's a different thing. However, by the way, note that to compute the integral of the absolute value of the function is much more difficult with tensor train than with Monte Carlo. The problem is reverse, because then you introduce cusps in the functions which are hard to deal with the tensor network, but Monte Carlo doesn't care, and it cares about sign. So the problems are completely reversed. Another interest, as was mentioned also before, is that by doing that, I have the full factorization of my integrand. So there are many things I can do as post-processing. For example, I want to compute this integral, but now I can do the full time dependence, because I can just restrict the integration domain after doing the factorization, and I get the full time dependence of my quantity in one shot, because the integration part is very quick. What's long is to build the tensor. The same way, I can multiply by time-dependent coupling constant. For if I want to not switch the interaction quickly, but make a smooth ramp, then I can just multiply in the integral and post-process that. That's an example where you have the charge of the quantum dot converging as a function of time, so the time dynamics for a small value of u here, for two different ways of switching the interaction, abrupt or smooth. And this is done by one calculation of tensor. And I want to insist on that, again, the choice of variable in your function is crucial. That was one of the questions whether the algorithm works. The algorithm works, it depends a lot about the choice of variables. If you choose the time differences, it works as advertised. If you just choose the time, well, here is what happens. The relative error is the green curve here as a function of chi. It absolutely doesn't work. We understand why. It's because all of these functions have heaviside functions, the green functions, retarded, advanced, all these Kelch formalisms. So when time crosses, there are cusps in the functions, and that's terrible for factorizability. It's hard to factorize heaviside functions, right? The change of variable put all of these problems at the boundary of the domain. So, choosing the right variable is crucial for the algorithm.
Olivier?
Yes?
I actually wanted to ask you precisely this. So you explain why, if you don't choose those differences in time, it's not going to factorize. But do you understand why it factorizes when you choose?
No. Well, partly. And that's how we came to this. When the time differences are large, we can see what diagram dominates, and we can find a form, and we can see it's an MPS. That's why we started by that, because we were using techniques, and then we realized that it factorizes everywhere.
You
Why?
Empirically realized.
Empirically.
Okay.
The good thing about this algorithm is quite robust. You have a problem, you put it in the algorithm, and you see whether your object factorizes. If it factorizes, good.
But
If
the
it
same
doesn't-
way that for ground states of, say, 1D Hamiltonians, we say area law, area
Yeah,
law.
yeah, it's an excellent question. I don't know.
You don't know.
And maybe there is, but at the moment we.
Do you have a sense for the range of validity of these?
Yes. So as I said, if the function has start to have cusps in your variable, that's bad. We
No,
know
I mean, you apply it to a given problem, but if we apply it to another problem, do you expect?
that's the last part of the talk. We don't know the honest answer.
Okay, thank you.
Strasco, does it mean the integrand has some special low rank property?
Yes. It has it at long distance, that we know, and it turns out that it has it. Why? Honestly, I don't really know. But maybe there is a good reason. Would be very interesting to know a priori. But so now to answer your question, what we want to do here is now, of course, to move away from this simple example. So there are different, of course, different kind of problem we can look at. Lattice problems, we want to go from one dot to a lattice problem. Imaginary time, as I said, quantum impurity solver are a natural target because they use, continuous time Monte Carlo uses a lot of, perturbative expansion to extremely high order. And there are more sophisticated versions of these. So one thing about what we did already is to do multiple quantum dots. So it's a start to do lattices. Instead, you have to, here is 2. So you have to sum over the time on some space dimension, a small lattice. And then immediately we run, it works. This is the same calculation. We take as a reference the converged value. Here, there is no, of course, exact benchmark. We see it converges slower than previously. And more importantly, it raises the question, how do I organize my tensor network? How do I put my variable? Do I put them together, like here, the first one? Do I put them one after another? I mean, we tried several ones, and some work better than some others. We don't really understand why. And the natural question is, can you do TCI for higher dimension tensors, PEPs or something? I don't know. Just, we need to think about this. It works, but it could probably work better. And to end on slightly newer results, we can do it for impurity solvers. So I want to do one calculation this time in imaginary time, totally different. And I want to do it for the continuous time quantum Monte Carlo, the CT hype, the hybridization expansion. So first, let me tell you what this is. This is the standard continuous time Monte Carlo for impurity problem, has been introduced by Philipp Werner in 2006. You have a quantum impurity problem, so a local problem with some, many orbitals and spins A, an atom with an atomic orbitals with whatever you want in it, Hund's coupling, Coulomb repulsion, complicated thing. And it's coupled to a free bars, which is represented by delta, the hybridization function here. What the algorithm does, it expands the partition function in power of delta to all orders. And that's explicit. You can write a formula for this because, it's the det of delta times a trace of atomic problems. And in practice, the algorithm will compute to up to an order proportional to beta, in practice, up to order 100 or 1,000. So we're not talking about order 10 here. But there is no exponential in these formulas. These are just determinants, so we can do that. And of course, it works beautifully well, but it has limitations, speed and sign problems. There are many problems we would like to solve where this has a terrible sign problem, especially when this delta matrix here becomes off-diagonal. And in practical terms, it means when you're trying to study, let's say with DMFT, a material which is distorted, which is less symmetric. And then you can be stuck. So can we replace this integral again by TCI? And the answer is yes, so that's work which is in preparation. It's done with André Erpenbeck from the group Emmanuel Gould at Michigan. And here are some results. Here, the calculation is done for a one-bond problem at moderate temperature for a non-interacting case, which for this expansion is a non-trivial test. You can see here the green function as a function of time. The different colors are different truncation of the perturbation. series. So you increase your order perturbation from 0 to 15, and the dashed line is the exact result. So you see that it does converge with 15 orders. We can compute the integral with 15 orders. We can do the TCI. It converges, it sums, and it gives the correct results. To do that, we need another change of variable adapted to imaginary time, which is sketched here, but I don't have much time to talk about it. Here we can see the convergence for different order, as a function of order for different rank. We see that it will converge. There is no real scaling at that stage because we don't, we don't really see. Or as a function of rank for different orders. If you cut at order, let's say 10 or 20, you will reach a plateau because you have truncated your series, but you will decrease, more and more up to, you have exhausted your series. The point is that the partition function is an exponential series. It does converge. It has no convergence problem. You just need to compute enough orders. So the problem that it raises here is to do TCI on a tensor of size several hundred and being able to control it. Here we're doing it size of order 30, so we do intermediate temperature. Here is a full DMFT calculation done with this calculation. So that's a standard basic DMFT calculation on the beta lattice, the thing you find in the textbook. Versus the Monte Carlo, you see the Monte Carlo, there's a bit of deviation here in this log scale for some values of u, otherwise you don't see the difference because the curves are on top. So we can reach relatively interesting temperature. Now, the first point is, first, this is just the first step. In these regimes, Monte Carlo is still very efficient. It has no sign problem. So we want to, of course, push it now in regime where Monte Carlo dies, meaning multi-orbital cases, much lower temperature. We'll see how it goes. However, it has already an advantage compared to Monte Carlo, because here we compute the partition function directly, meaning the free energy, which is a difficult calculation. And it's a very important thing to have if you want to, to compute and to study the structure of a material. You want to have the energy, the free energy as a function of parameter of the lattice and all so on. And we want to have it that fast as well. Right, so that brings me to my conclusion. So what I wanted to say is that there is, in my view, interesting things to do with these tensor trains to compute various kinds of perturbation theory. How far does this go? Well, we'll see. Replacing Monte Carlo, it will give you a faster convergence, and it will be insensitive to sign problem by construction. And on this, I thank you for your attention.
Okay, great. We have a couple minutes for questions. So, Nicola.
Great talk. So you might have mentioned, but I didn't get it very well, I think. So you made this change of variable in time and then regularized the integral.
Yeah.
So there are some lines of research in quantitative finance where they do something similar. Instead of changing the way you do it, they do a Fourier transform of very weird function, but they have analytical insight how to do it. Have you tried different types of change of variable that maybe can regularize even better, has smaller rank on the MPS side?
We tried a few simple things. This one was the best, but not very extensive. But it would be interesting because clearly we can expect the convergence rate to depend strongly on the change of variable. Yeah. And how to find them better, optimize on that, something we have not really explored yet.
Thank you.
Mike?
I missed something in the beginning. So the U's were the time delays or time separations.
Yes.
You also had sums over X. Where did the sum over X's go?
In general, you have a sum over lattices in general perturbation theory, but the problem here is a local problem. There is only one position, so there is no sum over X. Yeah. That's why we start with this problem, because it's simpler. We deal first with the time, then we'll deal with the space in the second problem.
But you did show some preliminary.
Some preliminary, yes, where there is both.
Introduce X, right?
Yes. So in that case, where I do double dots, X is a position. There is a sum over X. And then you need to put X and time difference on your tensors.
And just to understand there better, each X would just run over, say, like
one or
small
two or
number
three
of
or n.
positions.
It's a finite system.
And
Yes.
then the subscripts are just about the fact that you're at a specific order n, so it like repeats. Is that right?
The n is the order.
The reason why you have x1, x2 is because you're up to like a
Absolutely,
certain,
yes. Like the times.
Great.
It's the position of the vertex in space.
Okay, great. Yeah, Luke.
There's a question here from online, and I guess this graph illustrates it. Why is the error not monotonic with the bond dimension? Why does it go up sometimes as you increase?
I don't know. I don't know. maybe you.
Property of interpolation.
Yeah.
You solve locally, you put the zeros locally, but not zeros by here globally. You change elements globally by one global step. So you can't really expect monotonicity in terms of norm or integral or any observable because you have the only monotonicity you have more zero elements. Oh, I'm sorry. The only monotonicity you really have more and more zeros, exact representation of your elements which you computed. But you can, by doing local optimization and putting local zeros, you change elements globally, and sometimes it reflects in a massive jump up. You have general declining trend, but not on every step, and that's the nature of how interpolation works.
And it will also depend on your starting point. I mean, the position, if you change the starting point, the curve will look different. The general trend will be the same.
I see. So nature of the interpolation algorithm.
Yeah.
Okay.
It would be great if it was monotonic.
Do we have one or two more questions, Joey?
When you have these high-dimensional functions, how do you decide what order to put those indices in the tensor train? Because presumably that makes a big difference.
Open question? You mean here?
Yeah.
For example, whether I alternate time on x, or I could put all the times on the x.
Yeah.
I don't know. It's just
an open question.
The rank will obviously be different.
Yeah.
And you can see here the two graphs. Maybe I was a bit quick, but I mean, we could, you have different convergence and different graphs if you put them in different ways, and the power law in which it decays as a function of n is different.
So how do you do it in yours? Do you just randomly choose?
We just choose a couple of them and just experiment.
Okay.
At this stage, it's a bit, empirical, experimental, I would say. The first question is, does it work?
Yeah.
That's exactly the question that Kafre was asking. Does it work on many cases, or is it just limited? So that's our first question. And so.
It's funny because if I had a matrix product state and it was the ground state of a 1D system, and I randomly swap loads of sites, I would get a terrible approach.
Oh yeah. But if you do the same here, but there is a similar property. If you start to swap them completely, you will have a terrible answer. And the reason is that your vertices, your time which are close should be close because they are linked by grain functions. So the further away you go, the smaller the term in the determinant will be. By the way, this is 0 temperature where the function is a very long tail. If you do higher temperature, the function is much shorter. So the difference between different ordering will be even more striking, I guess. Because your function has a tendency to put the vertex close to each other.
I think this needs to be the last question. So we have the break. Yeah.
Question from Gunnar Moller. A question is how to choose the grids on which the tensors are expressed. Do you fix the grid from the start, or can you refine them as you go along with the calculation?
We're talking about the one-dimensional grid, right? I guess.
Yes.
We fix them, but we do several calculations for different value of grids to check convergence. But usually that's not the issue because the 1D grid converges very quickly, typically exponentially. So, I mean, we checked by just doing a few. No, it's not adaptative. Maybe we could do that, but not yet.